The solubilities there.
So then if, how would you tell if it's more soluble then? If it
The one with the higher X value, which is the solubility.
Okay.
Because when this thing is dissolving,
Oh,
the MnS changes by X. That is the solubility of it. It's the concentration that dissolves.
Okay.
Yeah. Yeah, just solve for X. Anything else about that? Okay, so let's go on. We're going to move on to the common ion effect. I know I had a question about that on the reading quiz yesterday. And we talked about it a little bit, and this is the same common ion effect as what we saw in the last chapter when you're dissolving a buffer that's, dissolving an acid that's already in acidic solution or whatever. You just want to make sure that your initial concentration in your ice table accounts for that common ion. So let's take a look at number 35b. And I have several problems from the end of the chapter. I didn't bother looking to see whether these were the same as homework assigned problems. But you can just tell that there's a lot of different things that the Zoom dolls will do in terms of problems they can give you. So we're going to calculate the solubility of iron 3 hydroxide. Now the problem gives you, I think, 3 different solutions that you're dissolving this stuff is. Part A is dissolve the iron hydroxide just in water. Okay, so you do the, it's going to give off X amount of that and 3X amount of that, and then you do the calculations today. You wind up taking 4 through. But then B says a solution that's buffered at pH of 5. So we want to dissolve this stuff in a solution that has a pH of 5. What does it mean to have a pH of 5?
So you can find that out.
Yes. You know how this breaks up into iron ions and hydroxide ions? There is no iron in there initially. Is there hydroxide in there initially? Yes, there is. How much? What's the concentration of hydroxide?
Okay, well,
Yes. The pH is 5, making the POH 9, right? 14 minus 5. So if the POH is 9, the concentration of hydroxide is 1 times 10 to the negative 9. Spencer, would you uncover the shade there? Thank you. So this is what our ice table looks like. We do have an initial concentration of this. Now, there's a word that's in that problem that we don't want to neglect, and that is the solution is buffered. Remember what a buffer does? I hope so. It tries to resist changes in pH. So if the concentration of hydroxide is this, and it's buffered, what will it be at equilibrium? Pretty close to the same thing, no matter what happens, unless you just exceed the buffering capacity, which we're just dissolving some insoluble stuff. It's not going to do that. So when you see that it's buffered and you have an initial concentration of hydroxide, if it's buffered, keep it the same at the end. Even if this number changes, the hydroxide is not going to. So the equation is this: FeOH, taken 3 times yields, Fe, positive 3 plus 3 OHs. The initial concentration of this is 1 times 10 to the negative 9. That's 0 initially. We didn't care about that. Now, it is going to shift right because one of our products is 0. Does it shift right much? Take a look at this K value. How do you feel about KSP equals 4 times 10 to the negative 38th power?
That's basically
This number is dumb. It's stupid. 10 to the negative 38th power? Imagine 10 to the negative 38th.
not much to
Point
imagine.
37 zeros before you get to a non-zero number. That's ridiculous.
That's just dumb.
It's just dumb.
Yeah,
I'm not writing it down. It's dumb.
I didn't really understand.
I can't imagine it. I need a visual experience.
It would go across the entire board.
I know.
No, not sure.
So anyway, it's really, really small. And part of the reason that it's small is not because it's so very insoluble, but because that gives off 1 and that gives the number of particles. You remember when we're finding the solubility, we're taking the 4th root. Now the fourth root of 10 to the negative 38 isn't as dumb. Still kind of dumb though. Okay? So anyway, this number right here, we're assuming is not changing. Why? Because it's buffered. So we assume that the change there is 0. Even though there is a change, it's insignificant because it's a buffered solution. And remember, buffered means there's some acid, some base in there, and when there's more hydroxide in it, the acid in the buffer gobbles it up. The iron changes by the same amount as that because it's a 1-to-1 ratio. So this at equilibrium is X, the iron is, and then the hydroxide is 10 to the negative 9. The question is, what is the solubility of iron hydroxide? Can you solve for X?
Yes.
It's easy, really. We know the KSP. KSP equals 4 times 10 to the negative 38. And that's equal to X times 1 times 10 to the negative 9 cubed. I've had other people asking that question too. When you see this number, do you have to multiply it by 3? The answer is no. This 3 does not dictate what happens with these numbers. The 3 is there to tell you what the relationship is between those two. For every one of these made, you get 3 of those made. That's what the 3 is doing there. That doesn't mean that this concentration suddenly jumps to 3 times 10 to the negative 9. Okay?
I asked the exact same.
Can you do this one? Find X. That's what we're trying to solve for. Do it without a calculator.
No calculadora.
Basically,
X equals what?
4 times 10 is negative 11. Means you said it over the
how'd you get that?
I'll actually go on.
Yep.
How'd you do that without a calculator?
Oh, yeah, that makes sense.
Oh, okay, yeah.
I feel it.
This term right here is 10 to the negative 27th divided into 10 to the negative 38th. Yeah? So it does make a difference that we have some initial concentration of hydroxide. Even though this is an acidic solution.
Wait,
This,
where did you get the answer from? Sorry.
It's math.
the answer, we're solving for
Wait,
X.
no, I didn't mean it like that.
Yeah.
So X times that number cubed. That number cubed is 10 to the negative
Oh, that's
27
what I did wrong. Okay.
into, 10 to the negative 38. Everybody else okay with that one?
That would-
Kelly?
It's bad.
Felix?
What are you doing?
Yeah, it is, just like the 5% rule. Yep. Because this X term, this 3X term, is small compared to 10 to the negative 9. Yep.
I still don't understand why you don't multiply it by 3 in the whole area.
This thing, because it said it was a buffered solution, that means that the hydroxide concentration is going to stay constant. The pH is going to stay real close to 5, which means the hydroxide concentration doesn't change. Now, does it change a little bit? Yeah, but not enough to make a noticeable difference in the number. As long as it's buffered, keep the hydroxide concentration constant. If it didn't say it was buffered, then you have to consider the plus 3x. All right? Anything else about that one? Let's move on. I'm going to ask you to try one. Would you try this one? Earlier I said it's going to stay at this unless you exceed the buffering capacity, which means if you add an excess of hydrogen or hydroxide, then it will change the pH. A buffer doesn't just keep the pH constant no matter what. I mean, if you add enough strong acid or base, it affects it. That would be like past the equivalence point. That's no longer a buffer.
salt for the picture this chapter?
It's crystals dissolving in water.
Okay.
Salute.
Do you get what we're doing?
I can help you.
Bless you in Mexico.
We're doing the salad
Not
with
Mexican.
potatoes.
Excuse you.
Oh, me and Felix did that one together.
Potatoes.
It's so bad. He tried to make us do bananas, but bananas didn't, like, even when you crushed them, you didn't get any, like, juice out of them, so it was just weird.
How long did you take?
All right, did you get an answer for this one?
You any good?
Did you?
Ooh.
Yeah.
Did you cube the 3x term? And from that get 27x cubed, not 9x cubed. That's a very common mistake. 3 times 3 times. Yeah?
Eric
Caught
goes
ya.
and fixes
No,
it.
I forgot to add the point 2 number already.
Okay, now, this makes a difference too. See this 0.2 plus 2x quantity squared? Do we hope to use the 5% rule and forget that plus 2x? If we keep the plus 2x, we've got a 5th order polynomial. Let's not use the point plus 2x term. Because it is a real small k value. That means x is going to be small, and that 2x is not going to affect the 0.2. It's not going to change the 0.2 enough. That makes it nicer. So we're just going to square the 0.2 and then keep that in the calculation. So get an answer for x. The question is, what is the solubility? So we're calculating this thing right here.
Why was that?
There's a lot of clumsier things I could do. So x equals what?
2.79 into
I'm going with 2.8. Just keep it in 2.6 times 10 to the negative 11. Sounds good to me. How about to the rest of you?
I like it.
I got 2.3.
What?
Wow, Jessica Tan.
What did you
Good
do?
thing I didn't use pen.
27, Jessica?
Did, oh, no.
No, dude,
Well, then it was times 0.2
Wait.
I agree with her answer.
Isn't it 0.2 squared?
squared.
It's 2.3.
Oh, wait, I
Squared?
forgot to cube
Yeah.
3.
You didn't
I mean, that
2.3.
makes a difference.
I didn't actually do the problem.
Yeah,
I thought
I think we got it wrong last hour. I think I was using 2.8. 2.3 times 10 to the negative 11. Are we good with that one?
Last hour couldn't agree on what power of 10 to use.
But that was 2.4.
Or what degree, I'm sorry. Excuse my math terminology.
Are we still debating?
Get that answer.
So 27.
Got it, Jessica?
You want this back?
Wait, just got 1.2. Oh my god. Okay, here.
Alright, I got 2.3.
You're teaching us the concept of rate
Yeah, I
determining
got it,
step,
got it.
Jessica.
I get it. Yeah.
Go ahead.
Wait, I forgot to square the 0.2.
Yes. Yep.
Jessica, it's not your day
Be
today.
careful. Now, is anybody thinking this concept is overwhelming and difficult?
No.
It's very easy. But it's easy to make mistakes too, isn't it? So be careful and you'll be fine.